Okay, here's some more examples of solving a quadratic equation by completing the square. And usually if the coefficient in front of the x squared is 1 and the coefficient in front of the x term is even, that's a great candidate for completing the square. If it's odd, usually it's a better candidate for using the quadratic formula, which we'll discuss later. But we're going to try this by completing the square anyway and see how it works. So what we'll do first of all is we'll isolate the x squared and the 5x. I'll just subtract 3 from both sides. So I've got x squared minus 5x. And if I subtract 3 from both sides, that's going to be equal to negative 3. And then we know that this is we're going to create or build a trinomial square. We know the square root of x squared is x. And then we always want to find half of this number in front of the x, as long as the coefficient is 1. So what's half of 5? Well, if you ever want to take half of a number, just divide it by 2. Half of 10 is 10 divided by 2, which is 5. So it's just going to be 5 divided by 2. And we know if we add these, we get 5 halves x, and if we take double that, we've got 5x. So that's our middle term, so that satisfies the conditions to build a trinomial square. So what I'm going to do is I'm going to add the square of this. This is a method. 25 In other words, 5 halves times 5 halves is 25 fourths. 5 times 5 is 25. 2 times 2 is 4. And I'm going to add that to both sides. Now I know I have a perfect square trinomial or a trinomial square. This is a perfect square. That's its square root. This is a perfect square. That's its square root. And we have twice the product in the middle. So I'm just going to factor to be something like this. This is my sign. My sign comes from here. It's the same. And just these little numbers go in here. X and 5 halves. Now I'm going to simplify this over here to save myself a little room. Negative 3 is the same thing if I put a common denominator, because we want to get these over a common denominator. It's a little bit easier than working with a mixed number. So negative 3 is the same thing as negative 12 over 4. And just double check that. 12 fourths is the same thing as 3, so that's negative 3. And then plus 25 fourths. So now they're over common denominator. So 25 fourths minus 12 fourths is 13 fourths. So that's going to equal 13 over 4. Now we know if something squared equals 13 over 4, that's something equals plus or minus the square root of 13 over 4. And since that's a perfect square in the bottom, I can rewrite this as plus or minus the square root of 13 over the square root of 4, which is plus or minus the square root of 13 over 2. So that's going to be over on the right. And then I can just add 5 halves to both sides. So I've got x equals, if I add 5 halves, and then plus or minus. And rather than writing it like this or like this, I write it like that. The square root of 13 over 2. And since they have a common denominator, we could put them back over the common denominator and say that's the same thing as 5 plus or minus the square root of 13 all over 2. Either way is fine. Okay, let's try another one of these. Here's example 5. And this is negative x squared plus 3x minus 5 equals 0. Now, we know that this polynomial is, if we just looked at the polynomial, it's shaped like a u. I'm sorry, it's shaped like an n because this is a negative, n for negative, so it's shaped like an n. But since we have an equation now, we can multiply every term by minus 1 or divide both sides by negative 1, doesn't matter. So we change all the signs, so this is going to become x squared minus 3x plus 5. That's going to equal 0. So this is also polynomial, and it has the same roots. Okay, the only thing is this is shaped like an n, and this is shaped like a u. So they're going to kind of be flipped, but they're both going to cross the axis at the same time. So even though you've changed the shape of the polynomial, it will have the same roots. So you might have a u that might go like, an n that goes like this, and a u that goes like that, and they're going to go through the same, they'll have the same roots. Like these might be the roots. And this equation would be shaped like an n. And it could be something like that. But this equation would be shaped like a u, so it's going to be something like this, you see. So the graphs won't look the same except where they cross the x-axis. So that would be the x-axis. I don't really know where the y is. There might be a shift, but shaped like an n, and for negative, shaped like a u, because it's not shaped like an n, but they have the same roots. Okay? So we can multiply or divide by the same number. It'll change the shape, but we'll have the same roots, so we can do that. Now we've done that, it becomes a lot easier because we always want this to be positive, so that's an easy fix there. So again, as before, we'll isolate the x squared and the x term, so I've got x squared minus 3x equals negative 5. And as before, x, and I'll take half of 3, which is 3 halves. And that's what I'm going to square. 3 times 3 is 9, 2 times 2 is 4, so that's going to be positive 9 over 4 plus 9 over 4. So we're adding the same number to both sides. And now we know we've created a trinomial square, because if this is a perfect square, that's a perfect square. If we multiply these, we've got 3 halves x. If we double that, we got 3x in the middle. So I know this is going to, in fact, be something like and the same sign will be here, so this is going to be negative. This is the sign that goes in between these, and I'm going to have x squared. I'm sorry, x, excuse me. And I'm going to have 3 halves. The little numbers go here. That's why if you write them up here, you know exactly. Your answer is right here. X minus 3 halves. Okay? And we can put this over a common denominator, make it a little bit easier to deal with. So negative 5 is the same thing as negative 20 over 4, I believe. Yeah, 4 goes into 25 times. And if I add that to 9 fourths, negative 20 plus 9 is going to be negative 11 fourths. Okay? So I know that if I take the square root of something, I guess I'll write it over here. I should have maybe done that over there, so I'll write an extra step so you can see here, because this is going to be a little more interesting problem. So I know if x minus 3 halves squared equals a negative 11 over 4, then x minus 3 halves equals plus or minus the square root of negative 11 over 4. Now we have the square root of a negative number, which is usually a no-no, but we're going to have a complex solution on this one. And remember, whenever we have a negative under the square root, it's just like when you peel potatoes, what's the first thing you do? Well, you take out the eyes. So that's the first thing you do here, you take out the eye. So this is going to be equal to plus or minus I, and then that takes out the negative, times the square root of 11 over 4. And then if I add 3 halves to both sides, I have x equals 3 halves, and then plus or minus I. And then we can break this up. This is the same thing as the square root of 11 over the square root of 4, which is 2. In other words, if you look at that, this is the same thing. I can do it over here on the side. I'm running out of room here, so I'll just do it on the side. That's the same thing as the square root of 11 over the square root of 4, which is the same thing as the square root of 11 over 2. So I can rewrite that as I times the square root of 11 over 2. And we could leave it like that. Because when we have complex numbers, we like to leave them in the standard form. So I can rewrite this down here. We have a little more room. 3/2 plus or minus, and we would write that as the square root of 11 over 2. That would be our b, our complex part, times I. So when you have complex solutions, and you'll write them in the standard form, a plus, and this is plus or minus, bi. Okay? So I hope that makes sense. That's kind of a tricky one.